Okay, okay, let us resume the second part of the class. And okay, so these are some fundamental the properties of the integral, of the definite integral. So if you integrate a constant, you can just multiply c times b minus a, the upper limit minus the lower limit, times the c value. And the here in these two, that those two properties say you may consider the addition of two functions first, okay? And then you can integrate it. Or you can integrate those functions separately, and then you can add the value. When you multiply any number to a function, you can pre-multiply that number before the integration, or you can multiply that number after you calculate the definite integral. The subtraction is the same. You can consider the subtraction before the integration, or you can consider the subtraction after the integration of each function. So those are the properties of the integral. And one very useful theorem is the following. Given this function f, if you integrate that function from a to c and c to b, you can just combine these intervals into one from a to b. So in other words, when you consider the area in, okay, between a and c, and then if you combine the area between c and b, then you get the area between a and b. So number one, you get the integration of integral of f from a to c, integration of f from c to b, and that if you combine these two, you get the integration of f from a to b. Okay, so when I derive this using the figure, okay, then we have this. But actually, a doesn't have to be smaller than c. C doesn't have to be a value between a and b. Okay, so here in this, okay, so here c doesn't have to be a value between a and b mathematically. Okay, so mathematically, we don't require any ordering among A, B, and C. Okay, they can be any values in any order in magnitude. Okay, as long as this value and these two are the same, I can combine these two. And if f of x is non-negative, then this definite integral represented the area of certain region, so that the value must be non-negative valued, right? If f is greater than g, then if f of x is greater than gx on certain interval, then that means f of x minus gx will be non-negative. Then by property 6, the integration of f of x minus gx will be non-negative. Then property 4 says this integration of this difference will be the difference of the integral. So that is non-negative, which means the integration of f will be greater than the integration of gx. So if my f is bounded, if it is bounded by lowercase m and uppercase m, in other words, if my f of x is less than or equal to uppercase m, then by property 7, the integration of f of x from a to b will be bounded by the integration of m from a to b, but this is the integration of the constant value m that will give you m times b minus a. So this integral will be bounded above by m times b minus a. If my f of x is greater than this lowercase m, then that value will be, by a similar reasoning, greater than or equal to m times b minus a. Right? So we have this property. So we already considered those. Okay. So these are some simple formula, simple properties you should be familiar with. Okay, please. Okay. Yeah. Okay. So let me summarize what we observed so far. So if I integrate a constant from a to b, then that will be c times b minus a. If I have some c times f of x plus d times g of x dx from a to b, that will be the same as c times integration of f of x dx from a to b plus d times integral of gx dx from a to b. So this second formula just consider generalized property 2, 3, and 4. Okay. And then what was it? What was it? Okay. So if f of x, so integration of f of x from a to b, a to c, and c to b, then you get the integration from a to b. If I switch these limits, you get the negation of the integral of this. So as a special case, when I integrate at from a to a, it will be 0. Now, if your f of x is non-negative on the interval from a to b, then integration of f of x dx from a to b will be non-negative. So I can generalize that if your function f is greater than gx on the interval from a to b, then the integration of f of x from a to b will be greater than the integration of gx from a to b. And if my f of x is between lowercase m and uppercase m on the interval from a to b, then my integration f of x dx from a to b will be bounded by m times b minus a. So these are the formula introduced in this section. Some of them can be derived easily from the definition or the concepts combining the area. And please remember that this value is representing the area of the region bounded by the graph and the x-axis and two vertical lines, x equals to a and x equals to b. So they bound a certain region, and the area of the region is given by this definite integral. So that is the summary of this section. Now, we will consider two theorems of in calculus, I mean in this integration, which are very fundamental, and we name them as fundamental theorem of calculus. And this fundamental theorem of calculus has two types. The first one, okay, I'm not going to prove this theorem, okay, but so let me go to this theorem directly. You can read this slide yourself. And here is the first part of the fundamental theorem of calculus. So if, okay, so if f is continuous on the interval from a to b, then when I define a function gx by this, okay, by this function is not only continuous, but also differentiable, and the derivative of g is f. So what does that mean? That means this part shows that this part shows that the g function defined by the integral of f of t from a to x, that this gx is an antiderivative of f. Okay, so the function defined by this will be your, I mean, is one of the antiderivatives of the given function. Okay, so please note that my g is a function of x. X is a independent variable, and that x is the upper limit of this integration. So somehow, if I estimate, if I can find this f, I mean this g of x, then this gx will be your antiderivative. So this is the fundamental theorem of calculus, part 1. Okay. So when I say it is a function of x, then here my x is an independent variable. It is a variable. Okay. So when I vary this upper limit, you get certain function. Okay. And that function obtained by this definite integral will be an antiderivative of f. So that is the part 1 of the fundamental theorem of calculus. So, you can read the first example or the previous slide yourself. Okay, I'm not going to consider those slides. Those are trivial. So please read them. So find the derivative of this function g. So if that is my g, this is integrating some square root of 1 plus t squared, the function from 0 to x. So what does the fundamental theorem part 1 say? Its derivative is the function. So here, this part 1 of the fundamental theorem says this gx is an antiderivative of f of x. What is f of x? F of x is the integrand of this integration, the definite integral. Okay, so what is the integrand here? This is square root function. Okay, square root of 1 plus x squared is the derivative of this gx. That's what this part 1 of the fundamental theorem say. Then what does the second part say? If f is given, okay, and this f is given as a continuous function between a and b, and if I know that any antiderivative of lowercase f, then this definite integral is obtained by this value. Okay, so here, please note that f is any antiderivative of f, any antiderivative of f. Then the definite integral is obtained by f of b minus f of a. So please remember, the last section of chapter 4 introduced a table, right, showing some examples of f and their antiderivatives. Okay, please remember that when f is, for example, a constant, okay, or then what is an antiderivative of the constant c? I mean, for example, if I have a 1 which is x to the 0th power, then the antiderivative was just x function. When I differentiate x with respect to x, you get 1. So that means if I integrate 1 from a to b, this part 2 of the fundamental theorem says I can evaluate my x at these two endpoints. So if I evaluate f at b minus f of a, and since f of x is just x function, that is the b minus a. Now, in the previous section, we considered the several properties, and one of them says if I integrate a constant function 1, that will be that value times b minus a, right? So I could derive this result from the properties of the definite integral, which we considered in section 2. But if I use this part 2, I can simply apply this antiderivative information to get this definite integral. And if I use it, the calculation will be much simpler even when I have a little bit complicated function like x. If I have x function, antiderivative will be 1/2 times x squared. So if I evaluate my 1/2 of x squared at b and a and compute its difference, so that will be 1/2 of b squared minus 1/2 of a squared. That will be the integration of x from a to b. What if I consider, say, sine x? Antiderivative of sine is negative cosine. So if I integrate sine function from a to b, f is negative cosine. So if I consider this, you get the negative cosine b minus negative cosine a. So that will be the definite integral of sine from a to b. So if I know these antiderivatives, then it will be very easy to estimate this definite integral. You don't have to consider the Riemann sum. Okay. So as an example, another example, here e to the x. What is an antiderivative of e to the x? E to the x itself. So to estimate the definite integral of e to the x from 1 to 3, you just estimate uppercase the antiderivative at 3 and 1 and consider their difference. Since an antiderivative is e to the x, e to the 3 minus e to the 1 will be the definite integral of this problem. Of course, if you want, you may consider any other antiderivative, like you may consider e to the x plus 7. Okay, then f of 3 minus f of 1 will be e to the 3 plus 7 minus e to the 1 plus 7, and that will be, since this 7 can be easily cancelled, we get e to the 3 minus e to the 1. So the answer is the same. Okay, so you may consider any antiderivatives, any, and this second part of the fundamental theorem of calculus will be quite useful. It will be very useful, and as I said, this definite integral depends on the values of these antiderivatives at these two endpoints. Okay, endpoints. The f of b and f of a will determine the definite integral of f. So, as I said, if I define gx by this, then that is one of the antiderivatives of f. So in other words, when I differentiate g prime, you get f of x. And if I know any antiderivative of f, then the difference of the antiderivatives at these two endpoints will give you the definite integral of the function. So, as I said, the gx is an antiderivative of f. So, meaning when I differentiate this gx, you get f of x. Okay, so this is your gx. So if I differentiate gx, you get f of x. And part 2 says, if f of the uppercase f is an antiderivative of lowercase f, meaning f of t is the derivative of uppercase of f, then when I integrate f, lowercase f, meaning if I integrate the f prime from a to x, then you get this. Or if I integrate f prime of t dt from a to b, that is f of b minus f of a. So that is the second part of the fundamental theorem of calculus. So from now on, we will use this fundamental theorem of calculus to estimate the definite integral. So you need to remember the results of the fundamental theorem of calculus. This is very important. So these two are very important. So if you remember the table of section 4.9, and if you combine that table with this fundamental theorem of calculus, we can calculate the definite integral for almost any function in the textbook. Okay, so when I say definite integral, we integrated certain function from a to b, right? From say 1 to 3, like this. In this section, we want to consider slightly different approach. Okay. So when I consider the integration of f from a to x, then, or a to b, you get a certain value, certain number. Okay. And if I use the fundamental theorem of calculus, in order to estimate this definite integral, I use the difference of the antiderivatives evaluated at two different values, b and a. Okay, so this result will be a number. Now sometimes, and sometimes given f of x, the uppercase f, we want to find its derivative, and the derivative is a function, another function, not a number. So in a similar way, given certain lowercase f, we want to express certain antiderivative. Okay, so in order to express just an antiderivative only, not the value at a certain interval, we sometimes use this notation here without limits. Okay, here in this notation, the lower limit and upper limit are omitted. And we just have this lengthy s with f of x dx. So this notation is usually used, okay, to represent an antiderivative of f. Okay, use a most general antiderivative of f. And so without these limits, this integration of f of x without a and b, this notation is called an indefinite integral, not definite integral. So as an example, so this notation means this uppercase F is the an antiderivative in most general form. So this means the derivatives of F is F, and we use this notation, not okay, so we do not use this expression because, as I said, when I use this antiderivative, it must represent a most general antiderivative, not a specific antiderivative, but general antiderivative. So I need to add C, and this C is a must. Okay, so you must put this C after this, I mean, x cubed over 3. So if you just write down this, that is not correct. That is not proper answer. And in that case, I will subtract some points. So when I ask this, your answer should be negative. The answer should be negative cosine x plus some arbitrary constant c. Okay, so this antiderivative. So in this slide, this notation is used for a most general antiderivative of f, and that is called an indefinite integral. So you must put c, okay, after any antiderivative. So you should distinguish carefully between definite and indefinite integral. A definite integral is a number, whereas an indefinite integral is a function. Actually, it is a function in most general form, so that you must add a constant c. So since it is depending on c, this notation represents many different functions. Sometimes people say it is representing a family of functions, meaning depending on the value of c, the expression may represent many functions. So if I ask you this, okay, even though tangent x is one of the antiderivatives, you must add c to represent all the possible antiderivatives, or in other words, a family of antiderivatives. So this is the correct answer for this indefinite integral. You must represent, okay, all the possible antiderivatives by adding c. And if I ask you to prove this, I mean, then you must show that this tangent x plus c is an antiderivative of secant x squared. And please remember such trick, okay? And this is the repeated version of table 1 of section 4.9. Okay, we already considered most of them, okay? So you should be familiar with this. And I will assume that at least you memorize this relation between derivatives and antiderivatives, or at least you have this information on your cheat sheet. Okay, so once you have this, we should be able to find the definite integral or indefinite integral of many other functions. So, and as I said, we adopt a convention that when a formula for a general indefinite integral is given, it is valid only on an interval, on one interval. So even though I used this, and that is okay allowed in many fields of science or engineering or physics. Okay, as I said, this 1 over x squared function is defined on the whole real line from negative infinity to 0 and 0 to infinity. So the domain of this 1 over x squared function is this. Okay, all the real numbers except the 0. And as I said, on the negative part, you see the c value on the negative part may be different from the c value on the right hand side. Okay, but we, okay, people in science community usually use this single c notation, and you can even use this single c in the exam, but when you do the research, you need to interpret that expression as negative 1 over x plus 1 constant on, say, negative part, and negative 1 over x plus another c value on the right hand side. So this notation implies two different constants on two separate intervals. That's how we interpret that notation. Okay, but since everyone in the science community knows this situation, we use this single c to express some general constant for the indefinite sum to represent a family of antiderivatives. So if I ask you such question in the exam, you can just use a single c. Okay, but when you go back to your research field, okay, you need to interpret that f of x to imply this. Okay, so you have one c value on certain interval and possibly with a different constant value on different interval. Now let us consider this following example. So evaluate cosine theta over sine, the integration of cosine theta over sine theta squared. Now, if I split this expression as a product of 1 over sine times cosine over sine, 1 over sine is cotangent function. Sorry. This is not cosine, but cosecant. Sorry. And cosine over sine is cotangent function. And its antiderivative from the table is negative cosine theta plus c. Okay. Then how about this one? Okay, it is, even though it is not given in the table, if I rewrite this, so the integrand 2t squared plus t squared square root of t minus 1 over t squared will be 2t squared over t squared plus t squared square root of t over t squared minus 1 over t squared. And the first term will be just 2. The second term is just the square root of 2, which is t to the 1/2 power. And 1 over t squared is the t to the negative 2. Then please remember that if I differentiate t to the n plus 1 times 1 over n plus 1, you get t to the n. Okay, so using this information, antiderivative of this will be 2t plus t to the 3 half over 3 half minus t to the negative 1 over negative 1. So that is an f of t, and we want to evaluate this the antiderivative f at 9 and 1 and consider their difference. We want to evaluate this, right? Now, this one is simply denoted by this symbol here. So the expression here, and then we have a vertical line, and vertical line has a lower limit and upper limit here. Then this symbol just represents this. Okay, so for simplicity, we use this notation to represent f of 9 minus f of 1, where f of t is given by this. So this notation means we evaluate that expression at point 9 and evaluate that expression at point 1, and we'll consider their difference. So if I evaluate that expression at upper limit and lower limit and consider their difference, we get some number, and that is the definite integral. Okay. So if uppercase f is an antiderivative of lowercase f, then the part 2 of the fundamental theorem of calculus was this. And since the derivative of uppercase f is the same as the lowercase f, my integrand can be replaced by f prime to get this expression, and we already observed this moments ago, right? When I explained the fundamental theorem of calculus, right? So, so please please practice this fundamental theorem of calculus. Okay. In the midterm, we will focus on the derivatives and just a simple problem regarding the integration. But after the midterm, we will focus on the integrations. Up to chapter 10, we will focus on the integration, and you should be familiar with the table, this table, and the fundamental theorem of calculus part 2 in particular, so that if I give you any function, you should be able to calculate their definite or indefinite integral. Okay, so we will have some problems in the midterm. Okay, we will have some problems, but there will be more problems, and after the midterm, the problems may be a little bit more complicated than those in the midterm. So you need to practice. Okay, you need to practice the integration now so that you can get used to this integration procedure. Okay, so please practice. Now, now we learned many uh, theorems regarding the differentiation. So for example, we consider the chain rule or product rule or quotient rule, right? So what was the chain rule? if I have the composite of two functions, f of g of x, then Taylor says the derivative of this composite will be the derivative of the outer function evaluated at gx multiplied by the derivative of the inner function. So that was the chain rule. So which means if I interpret this in terms of an antiderivative, so f of gx x, if that is differentiated, then I get this. So that this is an antiderivative f prime of gx times g prime of x. In other words, if I consider indefinite integral of f prime of g of x times g prime of x dx, you get f of g of x. And many people forget this g prime of x. Okay. And g prime of x is needed, right? Because that was the main result of the chain rule. When I differentiate the composite of f of g of x, you get f prime of g, not only f prime of g of x, but also g prime of x, right? That follows. So f of g of x is an antiderivative of this product. Okay. So indefinite integral of f prime of gx times g prime of x dx is f of g of x, right? Of course, I need constant though. Okay, so this is important. So as an example, since I don't have much time, so let me just consider some example. So if I have sine x squared, if I differentiate this, you get cosine x squared multiplied by 2x. This 2x is the derivative of x squared. So that means the indefinite integral of cosine x squared 2x dx will be sine x squared plus c. Okay? Or if I have e to the, say, sine x, if I differentiate this, you get e to the sine x times the derivative of the inner function, which is cosine. So that means e to the sine x times cosine x dx will be e to the sine x plus constant c. So I must have cosine x here or 2x here. So if you claim then it is wrong. Okay? Please be careful. And on Wednesday, let me continue this section and then I will show some examples of the problems on next Monday. Okay? Okay. Thank you for listening. Let's call it a day here and see you on Wednesday.